Uh, Hi everyone, this is ECE 111 Lecture 13, Blockchain Bitcoin Hashing, and we're going to talk about the final project, Set 1. Uh, so this is the Set 1 is blockchain and Bitcoin hashing concept. There's been a lot of talks about blockchain recently in the past 4 or 5 years or so. And this is a concept that has been around since 91, but it was not really the conceptual concept didn't really get materialized until about 2009 when Satoshi actually made this concept of a blockchain or cryptocurrency that has become suddenly very popular, and that's actually a just a fake name. Most likely we don't know exactly who reintroduced this concept of the digital currency, but what this blockchain is, it is, you could think of it as a chain of blocks, as the name implies, but the chain is actually provided by cryptographic transactions, and actually indeed it is provided by hash chaining. We've covered hashing before in the class, so you should be familiar with the hash crypto concept. What the blocks in a blockchain have is that they have a piece of data, they have the hash of that piece of data, and they also have a hash of a previous block. Now, as you could see, this is all chained together because the hash of, each block contains the hash of the previous one. So it's actually chained to the first one. Obviously doesn't have anything to chain to, and that one is called the Genesis block, just for your information. And now what happens is that every time there is a digital transaction, that digital transaction is going to be added to the chain of transactions out there. Imagine just an example, like I'm giving one I'm giving some money from my account to Bob's account, and that amount of money that is given from my account to his account is going to be subtracted from my account, is going to be added to his account, and also we have to readjust how much money there was in our account. And to begin with, we have to verify that if I have enough money to deposit that amount of transaction to Bob. Now, the amount of transactions, and the data about this transaction, such as the date, time, dollar, who I am, and what is my account information, and what is Bob's account information, are going to be in each of the blocks. But what happens is that in addition to that data, I'm going to have a hash of this data that determines in a standardized format that determines which of these data is going to be in each of the blocks. Now, I'm going to also have a signature of the block that is generated by cryptographic hashing. And once you chain these, because of the properties of the hash we discussed before, this data that is in the chain cannot be changed again. And this is called the process of immutability. Of course, never is a strong word, but what we mean by never, usually in cryptography, in every type of crypto you could imagine, is we mean that the probability of it is super low, so it's not possible within the computational limits of what we have at our expense, is not possibly be done. And the property of the blockchain and why it makes things independent of a centralized concept that had such as a bank is that data in the chain is available to everyone to see and to buy, and the record changing what has happened is difficult. That's not that's going to provide some level of a trust, and it's a distributed and decentralized, so it's actually a democratic way of for those centralized entity like a bank that takes into account everything. So this is just an example of how this blockchain is dependent on the hashes. We've talked about the cryptographic hash function. It takes an input, and no matter what the size of the input is, the digest is a fixed size digest. And if you change only one character, it's just going to generate a significantly different value for a small change of the input. You know, we've talked about SHA-256. You should have by now implemented and even optimized these properties. And the hash, just a reminder, the hash value is deterministic. It is a space, collision resistant, pre-image resistant, and so on. And last but not least, it should have the avalanche effect, meaning that changing one bit in the input should by by exactly 50% probability change each and every bit in the output domain. This transaction logs that are blocked, they're chained together, are called a distributed ledger. And it is basically having so different entities on the network are distributed entities are taking log of this ledger, and each of these blocks can contain about 1 megabyte of data. And the Bitcoin blockchain is significant because it's the oldest one in existence. Since then, there has been a lot of cryptocurrencies that have been introduced in various domains, and they have different values and different usages, but Bitcoin remains to be the most popular one because it was the first one. And the data on the Bitcoin blockchain is just has every transaction that has been done on the Bitcoin transaction. And this is really important because if we have these things chained together and this verified throughout the history, just changing everything, if you want to change, or if somebody wants to basically have a tamper with this record, that would be super hard. Now, the blockchain works like this. The first block registers 2 coin transactions and T2 between Damien and George, for example. The signature is generated for block 1 using the hash algorithm. Now, say is going to be sent to block 2 in block transactions, T3 and T4, and basically it's going to generate a new signature that is a function of the hash of the previous block, which is x32, and T3 and T4 transactions. So let's assume that this new signature is 9BZ as it's shown here. So you see here that this x32 is copied here, and now it's used within this block, and the hash is a function of the x32 and the content of this block. So again, this 9BZ is chained into the third block of transaction, and this chain of block continues over time. Now, let's just see what happens if somebody is changing the transaction amount. Like, what if, Damien has paid George $100, but he claims later on that I paid actually $100,000, and wants to get some benefits out of it. And now, in this example, I guess I've written 500 instead of the 100. And the thing is, if you change one bit of data from 100 to 500, you would be generating a new signature for block 1. So this new signature wouldn't pass the signature that was previously added to block 2, and then these two are no longer chained together, and that is not going to work for chaining this transaction in a blockchain. So the transactions on the chain should be unchangeable. And basically what happens is that it is not just, the block 1 is going to accept or reject block 2. It is all these other distributed observers on the network in this peer-to-peer network fashion that are going to verify the validity of the block 1 and block 2 and their transaction. So how is a block is accepted? It's actually based on the computational power of the parties involved. In fact, every 10 minutes or so, this acceptance of the blocks can occur, and this signatures can be accepted. So the first of all, a block will only be accepted if the digital signature starts, for example, in this example, 7 consecutive number of zeros. And what that means that the signature should be smaller than a certain value, because and this is in the hash domain, where we don't have any control over what values are being generated. What it means is that these other entities are going to randomly generate values until they find a value that is smaller than that threshold, meaning that it has those number of leading zeros, and then this digital signature is going to be added. If the string of data block has to be changed repeatedly until we find the string with 10 zeros, which means that the number is smaller than a certain threshold. And because the transaction data and the metadata are staying the same, it's just a small specific piece of data that is being added to the hash, which has no impact other than changing repeatedly to find an eligible hash signature. This piece of data is called the nonce of a block. For those of you who may have seen this word before, nonce in cryptography means a number used once. It's a number that is actually publicly known, but it's a number that you can't use more than one time, because once you give it out, it's a random number that can be used in a crypto algorithm, but it's the secrecy or the security it provides lies in the fact that it's only used once. And it's a random string of numbers. And now what happens if if someone who's malicious is going to calculate a new signature that has this property, that has this they want to change a transaction in the middle. Now they have to generate a signature that is within that threshold. But remember, the amount of time and computing it takes for generating that is very high. So if they want to catch up with the rest of the network, because if they change this block, they have to change everything else that has been generated here. Now they have to have a computational power which is higher than all the other users combined, because all these other users in a distributed way are always computing, and that basically that asymmetry in the computational power between the malicious or potentially malicious user who wants to change the signature and all the other entities in the network combined makes sure that this bitcoins are verified and secure. Now they have to this linking of the blocks basically becomes really difficult, and then finding this becomes really hard. So the nodes in the network, what happens is somebody, let's assume that somebody wants to buy goods using a Bitcoin from somebody who's selling something and who's accepting Bitcoin instead of regular money. Now there are all these other Bitcoin miners in this particular example. I'm putting Flint, Eric, Alice, and Greg, who provide service to John, and John's new Bitcoin is going to be added to the blockchain by generating hash for this block and meeting the required acceptance threshold. Now, this 4 people who are in the network in this example are going to generate these values on and on until one of them able to generate the hash value meeting the criteria. And then the first person to generate the hash value will be successfully to add John's transaction to the blockchain ledger and collect a service or reward fee. Now all the other miners will update the new blockchain because they get this nonce, and they're going to continue this. And this miners are invested in this transaction because they're putting this computational power into doing this transaction. So this is basically another depiction of this Bitcoin blockchain method and the distributed entities involved. And all of them have access to this public ledger, which is the record of all the transactions done on the network that are all chained together. Now, in the next set, we're going to talk about, now that we know the mechanism for doing this and we have built a SHA function before which does hashing, in the next slide set I'm going to talk about the details of the project and what is it that we're going to do for Bitcoin hashing in the project using the hash value that we have built before. Okay, stop.